Introduction and Common Myths. Welcome aboard Skylens, where we explore the science and stories of aviation. Today we're answering a question that worries almost every passenger at least once. What if every engine on a big passenger jet suddenly quits? Movies love to show a terrifying plunge, but reality is far less dramatic and much more interesting. Let's start with a crucial fact. A commercial jet is not a falling brick. Even with all engines off, it's still a well-designed glider. Modern aircraft have long, efficient wings that create lift even without thrust. Pilots train for this exact situation in simulators many times a year, memorizing checklists and practicing the emergency glide procedure until it becomes second nature. In this video, we'll walk step by step through what pilots actually do the moment engines fail, how a jet keeps flying, what passengers would feel, and how crews bring everyone safely to the ground. We'll also look at famous real-world examples that prove how well these procedures work. So buckle in, because by the end you'll know that a total engine failure, while rare and serious, doesn't mean doom. It means the pilots start a carefully rehearsed plan, and you're still in capable hands. How a jet glides without engines. When all engines stop, a commercial airliner doesn't instantly drop. It transforms into a carefully engineered glider. The long, swept wings you see from your window aren't just for cruising at high speed. Their shape and size are perfect for maintaining lift even without thrust. Engine power normally pushes the aircraft forward, but the moment that power disappears, gravity provides the forward motion needed to keep air flowing over those wings. Pilots immediately aim for the best glide speed, the specific airspeed that gives the greatest forward distance for every foot of altitude lost. This speed is calculated for each aircraft type and is memorized by crews. For most large jets, the glide ratio is around 15:1, meaning that for every mile the plane descends, it can travel roughly 15 miles forward. From a cruising altitude of 35,000 feet, that's more than 80 nautical miles of potential range. You might wonder about systems that rely on engine power, hydraulics, instruments, and electrical equipment. That's where backups shine. Batteries handle critical avionics, and a small fold-out wind-driven propeller called a ram air turbine automatically deploys to generate emergency hydraulic and electrical power. The pilots still have full control of the ailerons, rudder, and elevators, so steering feels normal. From a passenger seat, the difference is surprisingly subtle. The cabin becomes quieter as the engine roar fades, and you may notice a gentle, steady descent rather than a sudden dive. Seatbelt signs might illuminate, and lights could dim slightly to conserve battery power, but the ride itself usually feels like a typical glide toward landing. During this time, pilots are already scanning their navigation displays, calculating which airports, long roads, or even open fields lie within the wide glide circle. With more than 15 minutes of flight time available from high altitude, they have room to plan, talk with air trafficker. Pilot emergency checklist. When the last engine winds down, the cockpit becomes a calm but highly focused workspace. Pilots immediately follow a well-rehearsed sequence known as aviate, navigate, communicate. Aviate comes first. The captain keeps the aircraft perfectly stable and trims it to the previously calculated best glide speed. This is critical. Holding that precise speed preserves valuable altitude and maximizes the distance they can travel. Next is navigate. The first officer begins scanning the flight management computer and onboard charts to identify every suitable landing site within the wide glide circle. Modern avionics can quickly show which runways or emergency strips are reachable, and controllers on the ground can confirm weather, runway length, and terrain. Finally comes communicate. The non-flying pilot radios a clear mayday, or sometimes a pan-pan call, giving altitude, heading, and fuel status. Air traffic control responds by clearing nearby airspace and lining up rescue services while suggesting possible diversion fields. While these three steps unfold, the crew also works through a detailed engine restart checklist. They check fuel valves, ignition switches, and the position of throttles. If altitude and airspeed allow, they attempt a windmill or starter-assisted relight. Turbofan engines can sometimes restart if the initial problem was momentary, say, a brief fuel interruption or a temporary compressor stall. Cabin crew are briefed at the same time. They secure loose items, confirm that passengers' seatbelts are fastened, and quietly prepare for a potential non-standard landing. Non-essential electrical systems are turned off to conserve battery power, but critical instruments remain active, fed by backup generators or the small ram air turbine. All of this typically happens in just a few focused minutes, often so smoothly that many passengers remain unaware anything unusual is happening beyond the quieter cabin sound. Real causes of total engine failure. A complete loss of all engines is one of the rarest events in modern aviation, but it has happened a handful of times. Understanding the causes shows why the industry has become so effective at preventing it. Fuel exhaustion or miscalculation is the most common factor. In 1983, Air Canada Flight 143, nicknamed the Gimli Glider, ran completely out of fuel due to a metric conversion error. Despite silent engines, the pilots glided a Boeing 767 safely onto an abandoned airstrip in Manitoba. This event reshaped airline fueling procedures and cross-checking rules. Bird strikes are another threat. The famous U.S. Airways Flight 1549 lost power in both engines when a flock of Canada geese hit shortly after takeoff from New York's LaGuardia Airport in 2009. Captain Chesley "Sully" Sullenberger and his crew executed a flawless water landing on the Hudson River, saving everyone on board and setting a new benchmark for emergency training. Less frequent but equally serious is volcanic ash ingestion. British Airways Flight 9 in 1982 flew through a cloud of microscopic ash from Indonesia's Mount Galunggung. The ash sandblasted the engines, extinguishing all four. Pilots repeatedly attempted restarts and eventually succeeded after descending out of the ash plume. Another dramatic proof of careful crew action. Severe icing or catastrophic mechanical failure can also choke engines, but modern anti-icing systems and intensive maintenance inspections have made such cases extraordinarily rare. Today, jets carry redundant pumps, multiple fuel filters, and sophisticated sensors that alert crews long before conditions reach a critical point. These stories demonstrate two key truths. Total engine failure is extremely uncommon, and when it does occur, thorough pilot training and evolving safety technology have repeatedly turned potential disasters into celebrated examples of aviation skill and resilience. Passenger experience. From a passenger's seat, a total engine failure is far less dramatic than most people imagine. The first noticeable change is silence. The deep roar of the engines fades, leaving only the rush of air outside the fuselage. Cabin lights may dim slightly as the aircraft switches to backup electrical systems, but this is part of the plan, not a sign of danger. Instead of a sudden plunge, you'd feel a gentle, steady descent. Pilots immediately set the airplane to its best glide speed, so the nose lowers only enough to maintain airflow over the wings. The sensation is similar to a routine descent before landing. Air pressure in the cabin remains stable for quite some time, because the existing pressurization bleeds off gradually. Within minutes, the captain or first officer will make a calm announcement explaining the situation. You might hear words like, "We've experienced a loss of engine power and are gliding to a safe landing. The aircraft is fully under control." This reassurance is deliberate. It keeps everyone informed and helps prevent unnecessary panic. Flight attendants then move methodically through the cabin. They check that every passenger's seatbelt is fastened, secure loose items, and give a concise safety briefing. If the chosen landing area is unconventional, perhaps a long field or water surface, they may demonstrate a brace position or review life vest instructions. Because the airplane is still aerodynamically sound, turbulence or vibrations feel no different from a normal flight. In fact, many passengers on past engine-out flights reported thinking they were simply descending early until they heard the captain's announcement. The key takeaway: while the idea of all engines off sounds terrifying, the actual in-cabin experience is surprisingly calm and controlled, a testament to both aircraft design and professional crew training. Landing without power. After stabilizing the glide and selecting a landing site, pilots face the most demanding phase: executing a power-off landing with precision. Without engine thrust, there's no go-around, so every decision must be correct the first time. The crew first evaluates all available options within glide range. A long paved runway is ideal, but wide highways, open fields, or calm bodies of water are also considered. Air traffic control helps by clearing nearby airspace and relaying wind and weather data for each candidate site. If an airport is reachable, controllers may even activate runway lights or emergency vehicles in advance. Pilots plan a constant descent approach that requires no last-minute power changes. They carefully monitor altitude and distance, adjusting pitch to stay on the perfect glide path. Because drag management is crucial, flaps and landing gear remain retracted until the aircraft is certain to reach the touchdown point. Deploying them too early could shorten the glide and force an undershoot. As the target draws near, flaps are extended incrementally to reduce speed and steepen the descent, followed by lowering the landing gear. The goal is to arrive slightly high and fast, allowing a controlled flare just above the surface. This flare gently raises the nose so the main wheels touch first, absorbing energy while preserving directional control. Once on the ground, or on water, as in the Miracle on the Hudson, pilots use spoilers and manual braking to slow the aircraft. Reverse thrust is obviously unavailable, so accurate speed management on approach becomes critical. Meanwhile, cabin crew guide passengers through final brace positions and prepare for a rapid but orderly evacuation. Even in silence, the entire process is a display of teamwork and practice skill, proving that a safe landing is achievable without engine power. Lessons and future safety. Every incident of total engine failure becomes a powerful lesson for aviation worldwide. After each event, whether it's a fuel miscalculation, volcanic ash encounter, or massive bird strike, investigators from agencies like the NTSB, FAA, or ICAO conduct a thorough, months-long analysis. Their reports identify the smallest contributing factors: maintenance procedures, crew communication, and even how checklists were followed under stress. These findings drive continuous improvements. Airlines now use ultra-precise digital fuel monitoring systems and require multiple independent calculations before a flight leaves the gate. Engineers design turbine blades with advanced alloys to resist bird impacts, and airports invest in sophisticated radar and habitat management programs to reduce bird activity near runways. Pilots receive recurrent simulator training that includes complete power loss scenarios, ensuring that muscle memory guides them when seconds count. Technology is also evolving toward prevention. Modern airliners feature multiple independent electrical and hydraulic systems, so essential controls remain operational even if all engines stop. Next-generation engines include automatic restart capabilities and sensors that detect icing or volcanic ash before a human crew could react. Research into hybrid electric propulsion and fuel cell systems hints at a future where aircraft might glide on backup electric power rather than rely solely on traditional turbines. Perhaps the most important lesson is psychological. Passenger safety depends not just on machines, but on training and teamwork. The Miracle on the Hudson, the Gimli glider, and similar stories show how disciplined crews can turn a potentially catastrophic failure into a textbook example of aviation skill. Today's pilots study these cases in detail, carrying forward the knowledge that quick thinking and calm action save lives.